Hey, this is for Chapter 6, Modeling Random Events, the Normal and Binomial Models. And more specifically, we're looking at Chapter 6.1, Probability Distributions are Models of Random Experiments. In previous chapters, we studied distributions for both numerical and categorical variables. The following is the distribution of the ages for the players of the New England Patriots in March 2016. And the source is given here if you'd like to check out their website. All right, so what we can see from this histogram is that the ages are displayed on the horizontal axis, so that's our variable. And we can take a closer look at the scale given. So we've got 25 marked and 30 marked, and notice that there are, 1, 2, 3, 4, 5 bars in between them. So we know our scale is, each bar has a width of 1. So it means if we count back, this is 24, 23, and 22. So notice this distribution shows us all the possible ages of the players on the team at that time, as well as the frequency. So for instance, we know the 22-year-old players, there were 8 of those. All right, the distribution above gives us the ages of the players on the team, as well as the frequency or number of players at each age. Another way to display this distribution is in table form, which is shown below. So notice that bar above 22 had a frequency of 8 that we can verify here. And the table also gives us one more piece of information. Shows us that there were 79 players. So if we add up all the numbers in this column, we would get a total of 79. Okay. On the next page, the distribution of the ages for the players on the the distribution of the ages for the players on the New England Patriots in March 2016 can also be displayed using the relative frequencies for each age. Relative frequency gives the proportion of the team within each given age. All right, so if we take a look at that first bar on the left, like we did on the previous slide, remember these were the 22-year-olds, because that bar went from 22 to 23, and again, only the left endpoint gets included, not the right-hand side. We look at the frequency given, the relative frequency in this case. Looks like it's about a hair above 0.1. And we can confirm this by taking the frequency or number of players with that age, dividing it by the total number of players. And we're going to find that that is indeed about 10%, or 0.10. All right, number 3. In this chapter, we're going to learn about probability distributions, which tell us the possible outcomes of a random experiment and the probability that each of those outcomes will occur. So if we consider selecting a player at random from the above distribution, then the relative frequencies give us the probability of selecting a player of a given age. The following is the probability distribution for selecting a player of a given age at random from the New England Patriots. So here is our probability distribution. Right here. These don't always include this middle column for frequency. Typically, they just include the first column, which lists the possible values of your variable, and the last column, which lists the relative frequencies or the probability that you would select someone of that age at random. So in that in mind, this also up here can be thought of as a probability distribution because it also lists the possible values of your variable, in this case, again, the ages of the players, and the probability that you would select one at random. All right, so down below at the here, we're going to look at these bullets. We use this probability distribution to answer the following questions. So first one, what is the probability that a randomly selected player is 26 years old? So we want the probability that your age that you pick at random is 26. All right, so we can go into our table here. Here's our 26-year-olds. There were 13 players that were that age out of 79, and if we convert that to decimal form, we should get this last number on the table. That's going to be approximately 16%, or 0.16. All right, second bullet. What's the probability that a randomly selected player is less than 26 years old? All right, so that means we want the probability that the age is less than 26. So that means we want to include all of these numbers here. So again, we've got two options. We can add up those 4 relative frequencies, or we can add up those 4 counts. If we add up those 4 counts, we get that there are 36 players out of 79, and that's approximately 46%, or 0.46. 6. Okay, and this third one, what's the probability that a randomly selected player is greater than 26 years old? So the probability that the age is greater than 26. It's going to be all of these numbers here. We either add those up or add up these counts. If we add up those counts, we'll find that it's 30 players out of the 79, which is approximately 38%, or 0.38. So a couple of things to note. One, if you add up these three fractions, you're going to find that you've accounted for all 79 players. If you add up these three percentages or decimal form, the proportions, you should again find that you've accounted for all of the players, 100% of them. Which means the total area under this probability distribution up here is 100%. All right, so note a probability distribution is sometimes referred to as a probability distribution function, or PDF for short. Okay, in Chapter 1, we classified variables as either numerical, such as ages, or categorical. For instance, did the coin land heads or tails? In this chapter, we need to further break the numerical variables down into two or more categories, discrete variables and continuous variables. All right, so as an example, discrete variables or discrete outcomes have numerical values that you can list or count. The ages we just saw would be an example of that because we were able to list the ages. We went from 22 all the way up to, I can't remember the oldest player, maybe 39 or 38. Okay. Continuous variables or continuous outcomes have numerical values that cannot be listed or counted because they occur over a range. So this may be something like weight or height, where you can't list it as just a set of discrete values. So we'll talk more about the discrete variables in our next class, and we'll see another example of continuous variables down below. All right, so in number 5, the ages of the New England Patriots were reported as integers and may be considered discrete. However, age could also be considered continuous. For example, if ages are not rounded to the nearest year, then any of the following ages are possible. So you could have someone who's exactly 26 years old, someone who's 26.01 years, or 26.000, a bunch of zeros, 9 years, etc. In that case, you're looking at it as how many years, days, hours, maybe even seconds old they are. All right, number 6. Following diagram, which is from page 250 of your textbook, illustrates the difference between discrete and continuous. So if we think of ages as discrete, think of it as steps, then someone is either 1, 2, 3, 4, 5 years old. But continuous, like a ramp, they might be 1 year old or 1.01 years old or 1.5. There's a lot more options. It's continuous, and that goes all the way up to 5 years old. All right, so know that for the staircase, you can count the number of stairs or outcomes, but for the ramp, you can't. On the ramp, there's too many outcomes to count. So number 7, the distinction between these two types of numerical variables is important because it will determine how we can display the probability distributions. The probability distribution of a discrete variable can be displayed as either a graph or a table. Probability distribution of a continuous variable can be displayed as a graph, but not as a table where each individual value is listed. Instead, what we'll see is that we would have to list a range or subset of the values. Okay, number 8, the following is a sample distribution of the heights of a sample of mothers. And the source is given below, so you can check that out if you'd like. These heights are considered continuous since the heights are not rounded to the nearest inch, which means that any of the following heights are possible. So you could have someone who's 62 inches tall, or again, something a little above 62 inches, or something even a little bit less above 62 inches. But anything in between, let's say 62 and 63 is a possible measurement or possible measure of the person's height. In other words, we're not limiting someone to just 62 or just 63 inches. All right, so here's our sample distribution. Notice that mother's heights are at the bottom, so we should put heights here to remind ourselves that this is the variable of interest for these mothers. Notice that your vertical axis is relative frequency, and so it's telling us the relative frequency of each range of values. So for instance, this first bar on the left, right here, and switch colors, make that a little bit more clear. This goes from 55 to 56. We check, that looks like our scale. I've got 57, 58, 59, and 60. So that first bar is all the moms that are above 55 inches tall, but less than 56, because again, that right-hand side endpoint is not included in that bar. And the frequency, or the relative frequency in this case, is 0.001, or 0.1% of the moms in this sample had that height range, or had a height within that range. All right, so this distribution gives us the heights of the women in the sample, as well as the relative frequency or proportion of women for each height range. If we present this information in table form, there are too many individual heights to list, so we instead provide the frequencies for each range of heights. Right, so notice we don't have a row just for 55, but we do have one for 55 to 60. So if we wanted to check that, we would have to go up to our histogram and include 55, 56, 57, 58, 59, add those up, and what we would find is that would give us a value close to this. It's going to be slightly different. I think if you want to press pause and double check this, you get something around 0.15, but that value from the histogram has been rounded quite a bit more. So this number from your table is more exact. All right, same thing can be done for this row of your table. If you wanted to verify that, you come into your histogram, add up the heights of all these bars between 60 and 65, and you would find that that is, again, pretty close. It's about 0.71. Same thing for this third row. Again, press pause, try this out. But 65 to 70 would include these bars from 65, 66, 67, 68, 69. And that, again, is just a little different due to rounding. So we'll make a note here that difference is due to rounding. Okay, and the last one's easy to check because that is just that last bar in your histogram. So again, that's 0.001 roughly. Okay, so just one last comment. Move on to the next page. Remember that this is a probability distribution. It's given in graph form at the top, and it's given in table form down at the bottom. And it's a probability distribution because it's giving you the range of heights and the probability that if you were to pick a mother at random of getting a mother of that particular height or within that height range. Okay, and so number 9, how do we find the probabilities for continuous outcomes? So we saw above, we can't list all the possible values we might see, but we can list the range of values we might see. So we can then find the probability that a particular observation is between two given values. So we're going to use the histogram to find the probability that a randomly selected mother has a height between 60 and 65 inches tall. So that's going to include this bar all the way, let's see, where's our 65, right up to there. So we're going to include all of this in the middle. So what we're really doing is looking for the area of all of those bars added together. So we want the probability that a mother's height is between 60 and 65. So we've got 0.12 plus 0.15, 0.17, 0.16, and 0.11. So if we add these up, we get about 0.71. Okay, so second bullet is probably the same as the probability reported in the table. Here's our entry for 60 to 65, and as we saw on the previous page, that is indeed roughly the same as what we get from our relative frequency histogram. Right. Taking a closer look at the probabilities in this table, we want to find what the sum of these probabilities are. So I'd suggest pressing pause and adding these up. And what you'll find is that it's very close to 1. So I'm going to put approximately 1. There's some rounding in this table as well. So if you did add them up in your calculator, you're going to see that it's 0.999. There's a lot of 9s in there. So you get very close to 1. Okay, and the last bullet, what is the sum of the relative frequencies in this histogram? If you add these up, again, you get very close to 1. If you've pressed pause and tried it out, you're going to find that due to rounding, it's actually a little bit above. So it's roughly 1.015. And again, from the histogram, this comes from adding up that first bar's height plus the second one plus all the way over to the end on the right. And again, since these are all rounded, you get a slightly different value than 1. Since it is a probability distribution, though, the sum of all of these relative frequencies should be 1 or 100%. Okay, number 10, a coffee shop manager is interested in finding the probability that a customer will wait less than 2 minutes to be served. The following probability density curve is a model of the histogram of wait times for our customers. This probability density curve shows the probabilities for this continuous valued random experiment as areas under the curve and has the area between 0 and 2 minutes shaded. So you can keep in mind that this is a model, so it possibly is showing you what the histogram looks like. So maybe they took data from a previous year and they created a histogram for it, a relative frequency histogram. And this curve is just giving a model for it. So it may be a great fit and maybe some slight differences. And so the question might be, where did the curve come from? Well, in practice, it's often difficult to know which curve is correct for real-life situations. And if they base this on previous data, they might have a pretty good idea. Key, though, is to remind yourself that it is a model, so it is meant to mimic a real-life probability, but you might not know if the curve is correct. Okay, so we're going to use this diagram to estimate the probability that a customer has to wait less than 2 minutes to be served. So notice that's your shaded area up above. So if we had our histogram, we would be adding up all those relative frequencies for each bar. But since we don't have those values, we don't have that actual histogram, we're going to have to estimate. So we want to know, what's the probability that your wait time is less than 2 minutes? So we can also say that's our variable is x, and what's the probability that x is less than 2? So from our graph, I would say that that is less than 50%. Looks like less than half of the area underneath the curve. In fact, maybe it's closer to about 45%. That would be my guess. And keep in mind, with continuous variables, we're actually treating this statement, probably that x is less than 2, the same as this statement, that probably that x is less than or equal to 2. So we no longer have the actual data. We can't distinguish between those two statements. So again, if we're just looking at areas under a curve, we're going to treat these two things the same way. All right, second bullet. Use this diagram to estimate the probability that a customer has to wait more than 2 minutes to be served. So the probability that x is greater than 2. So hint here is, what do you think the total area under the curve is? Remember that in a probability density curve, this total area should be 100%, because that means we've accounted for all of the wait times that are possible. So given that, and that this is a complement of what we just found, so these again are complements, that means that these two probabilities or areas should add up to 100%. So this should be 100% minus what we said above. So if you have a slightly different answer to the first bullet, you're going to have a slightly different answer to the second one. So we're going to say that this probability is roughly 55%. And again, the roughly here is just because this is an estimate from our graph. All right, so in practice, it's often difficult to know the exact shape of a distribution. For instance, how did the coffee shop manager know that the probability density curve given above was the correct shape? Manager hopes that this probability model resembles the histogram of actual wait times for customers, but can't be sure. The manager compares these predictions from the model to the actual frequencies from a sample of customers. Then she can determine how good the model's predictions are. So if she actually takes these actual frequencies, maybe she looks at data over a month or two, creates a histogram and recalculates, I shouldn't say recalculates, but comes up with the percentage of her customers that waited less than 2 minutes and the percentage of customers that waited more than 2. If they're fairly close to what our model predicted, then we have a good fit. Our model's a good fit of the actual data.